So the next thing we want to talk about is the electromagnetic spectrum and how this relates to energy from light. So we've got, on one end, I've drawn, or the picture shows, that is a pretty big wave. Whereas over here, we've got what is a really, really small wave. And so if you think about something that is slowly and casually kind of sauntering back and forth, doesn't take much energy to do. If you think about something that is vibrating back and forth like 1,000 times a second, that takes a lot more energy. That going back and forth really quick, that is this end of the spectrum over here. Whereas the sauntering back and forth, that's like this one, really big one over here. So red light has the lowest energy, and violet has the most energy. Now here's the thing, there is a whole other spectrum to this. I basically took that whole picture, and that only takes up this much of the actual spectrum. And this is also a logarithmic scale, which basically means that it's way bigger than it actually looks on this paper right here. So we do have other kinds of electromagnetic radiation, but here's the thing. I can see red light. So if you have light that is right here on this spectrum, I can actually see that. It shows up as red. My brain knows what to do with that. I cannot see radio light. And now I said radio light, which sounds kind of weird because when we hear light, we think like things you can see. This is the exact same idea. It's just that this radio wave is too low energy for my brain to be able to understand what's going on, whereas this red light wave is just enough that I can understand it. On the other end of the spectrum, I can look at the sky and I can see blue, and I can know, okay, that sky is sending me blue light. That fits in right about here. But if you make it just a little bit more to ultraviolet, I can't see that anymore. So it's still the same kind of radiation. It's just that my brain can't actually see that kind of radiation because my brain has never needed to. My brain has only ever needed to see this stuff right here, and that has kept humans alive for billions, millions, whatever, long time. On the other end of the scale, gamma rays, X-rays. I know, like, it kind of sounds like, well, wait, I can go to the doctor, I can see my X-ray. You are not actually seeing the X-ray itself. What the X-ray is doing is it is moving through all parts of you except for your bones. So let me draw. This is the picture. And so what they do is they shoot a bunch of X-rays at you, and it goes through almost everywhere. But when an X-ray hits your bone, it actually can't go through your bone, so it's going to come back. And then same thing when it hits your bone over here, it comes back. And all of that coming back part blinds the camera, and it turns it into just white. And so that's what you see as the white on your X-ray. Talking about radio waves. The way that this works is there's two different things you can manipulate. So there's either AM or FM. AM stands for you are modifying the amplitude, whereas FM is when you modify the frequency. So when we look at waves, if I back up a step, there's two parts of waves. When we talk about the amplitude, that is, so if that's my middle line, the amplitude is how high up do you go to get to either the bottom or the top. The frequency is how long is one wave. So when you listen to an FM radio and it's modifying the frequency, the way that the radio is actually telling your speakers what to do is it has these waves right here, And it would be like, so that is a relatively long wave, and then it would have a shorter one. It's not like super short, but it's a little bit shorter. And then the next one might be longer again, and then longer, and then shorter. And your radio receives that, and it knows what to do with that information. It's coded through like whatever transistors, however they work. That's not the right word. Anyway, your radio knows what to do with this. It plays a song. If you have AM, what it does is it keeps the frequency the same the whole time, but it changes the amplitude, meaning now it's going to go up higher. But it's still just as long. And then it goes up maybe somewhere in between. And so on. I haven't drawn this perfectly, but that's the way AM and FM radio works. We can send those into space as well, and then that's how we can relay messages back and forth, so that if someone is on the International Space Station, we don't have to wait for them to come home for them to give us all of their information on like a flash drive. There's no Wi-Fi up in space, but we can use radio waves to communicate like that. Okay. So when we have radio waves coming from, let's say, another planet, that can tell us something about that planet. Kind of like how light waves, like if we look at another planet through a telescope, we can learn stuff about the planet based on what it looks like. Same thing with radio waves, because it's all part of the electromagnetic radiation spectrum. They're essentially the same thing. Humans' eyes just aren't designed to see them. That's all. So if radio waves can tell us stuff, why not have radio telescopes? What do we say here? Better than opticals, like the ones that we're looking at with visible light, because weather doesn't matter. Doesn't matter if it's dark outside, because you can't see it anyway. And things in space, not all of them emit light. So let's say we had something in space that puts out energy, or puts out light, rather, at this wavelength. Maybe that is something that we can actually see as light. Let's say I had something else that was pretty much the same, except the wavelength was just a little bit longer. Now we can't see that anymore. So if we're only using telescopes that are optical, like the seeing kind, we're never going to know that this other thing even existed. Because it's not emitting light, we can't see it unless the sun shines on it, but that far out, it's not going to. If we use radio telescopes, we can now pick up this wave, and we can figure out, okay, there is actually stuff there. Same idea with interferometry. Works the same way. Okay, different kinds of waves. So these are not the visible kind. Infrared, that's where I'm going to start at. This is like heat energy. And so when we were talking about main sequence stars versus giants versus supergiants, we said you want to look at how much heat energy they're giving off and what color they're at, and that can tell you about like how old the star is, how much longer it's going to live for, how big it is, how much mass there is, those kinds of things. That we can all get from infrared, which is not light that we can actually see. It's a different spot on the electromagnetic spectrum, just more or just below where red energy would be. Microwaves, there are still microwave radiation going around from the original Big Bang. So if we can pick up on that, like when you get radio static, that radio static is there because your radio is picking up radiation from, well, there would be other things by now, but even if we got rid of all like cell phones and radio towers and everything, and you just had a radio, out in the middle of nowhere where there was no radiation, you would still have radiostatic from the original Big Bangs. There would still be some kind of radiation there. For X-rays, we said that visible light cannot escape black holes, but if we use X-rays, those have more energy. So they can get closer to a black hole than visible light could. And then gamma rays are just like the most energy. They're the highest energy, so they can do, I guess, the most stuff. When it says they've disappeared from unknown sources, like thinking about that one, if you have something that's just out in space and you can't see it, it's not giving you any radio waves, not giving you any microwaves, might be pretty tricky to know what that is. Gamma rays, the strongest ones, can tell you there's something there, and then you can try to figure out what it is, but they're tricky to work with because it's such high levels of energy.